variation parameters. Our goal in this section is to be able to solve the non-homogeneous differential equation by this method, variation parameters. So in terms of solving a differential equation, if it's non-homogeneous, the method that we have seen so far that can do that, if it's second order differential equation, is the method of undetermined coefficients. You've seen that in two parts. You could solve that in terms of what's called the superposition approach, or you could solve that method for undetermined coefficients by the previous section, the annihilator approach. I think the previous section, 4.5, for that method of undetermined coefficients, to me, seems to work a little bit better. For the superposition approach, you got to take into consideration the glitch in the system, and you have to trump up your y sub p. In 4.5, you don't have to do that. The method takes care of that with the differential operators. This method here, 4.6, does not deal with glitches. It does encompass the Warren scheme. The Warren scheme plays a major factor in solving the differential equation. So we seek to solve here equation number 1. And oh, by the way, I have to go and make some modifications in Blackboard, and I will try to make those changes today. In Blackboard, this section is probably called 4.7. In the old textbook last semester, it was 4.7, so here is 4.6. And then the next section, the Cauchy-Euler method, was actually 6.1 in the previous textbook. In this textbook, it's 4.7. So I make that change so that you won't be more confused than what you already are, right? So no. So we seek to solve equation number 1. This is a linear nth order non-homogeneous differential equation. What makes it non-homogeneous? It's that g of x sitting over there. It has here, this guy says constant coefficients, a sub n minus 1, and so on to a sub 1. Can the method of variation parameters be applied to a differential equation if you don't have constant coefficients? Yes, we can still use this method. So it's very powerful. So previously we solved equation number 1 by the method of undetermined coefficients. Today we use a different method. We seek to solve equation number 1 by considering the second order non-homogeneous differential equation. We want to be able to find solutions for equation number 2. Well, the way we try to solve it is to look at first the first order differential equation of the same type. That is, that differential equation that has highest derivative 1. See how that solution looks. I need to go over on the side to show you that. Here, to solve a sub 2 of x times y double prime plus a sub 1 of x times y prime plus a naught of x times y equal to here, say 0. To solve this, first consider the dE when n is equal to 1. That is, consider a sub 1 of x times y prime plus a naught of x times y equal to 0. Right, this dE in the form a times y prime plus b times y equal to 0. Just call the coefficient a sub 1 of x, just call it a, and the coefficient a naught of x, just call that b. Well, you recognize this, that this can be solved by separation of variables. And so this dE separation of variables. So here this is a times dy over dx plus b times y equal to 0. This implies that this is a dy over dx is equal to negative b times y. And so this becomes dy is equal to negative b over a times y dx. Let me get the y on the other side. Should have done that. I didn't see it. It's an a there. So this is 1 over y times dy is equal to negative b over a times dx. Integrating both sides, this implies that we have the natural log of the absolute value of y is equal to negative b over a times x plus some constant. Let's call it c sub 1. Exponentiate both sides. And so this becomes e to the natural log of y is equal to this e to the negative b over a times x plus c sub 1. And this gives us y is equal to some constant c times e to the negative b over ax and I've just had a brain explosion. So that is, I don't need this. Shoot, I don't need it. I don't need it. Okay. Maybe that's why I didn't put it in my lecture back over here. I don't need that. I'm thinking about something else. Okay. I got a lot of stuff going on. Sorry about that. Okay, I don't need that. Anyway, okay, it just took 10 minutes trying to go somewhere, and I didn't get anywhere. But anyway, I didn't need that. I didn't need that. Please forgive me. Okay. I don't have this all the time, so. Oh, boy. Woo. Okay, mercy, Lord, mercy. Let me get back to this. Okay. We seek to solve equation number 1. That's this guy right here. By considering the second order non-homogeneous differential equation, this guy right here, which I was getting there, but I don't need that. This is equation number 2 here. It's the same thing as number 1, but here n is equal to 2, the second order differential equation. How do we get from equation 2 to equation 3? Just divide everything by that a sub 2 of x. And so here the p of x is the a sub 1 divided by a sub 2. The q of x is a naught divided by a sub 2. We'll need q of x later on. We don't need it now. Here's the injection. The particular solution, y sub p, is written in this way. Now that's different than how we wrote y sub p before, right? This y sub p is written in this fashion for the method of variation of parameters. It will still give us the y sub p that we knew from before. And so here, he's introducing some parameters. It's called the method of variation parameters. What are the parameters? U sub 1 and U sub 2. What are U sub 1 and U sub 2? We don't know yet. We have to find out what they are. And with any problem that has parameters, you have to solve for the parameters. So U sub 1 and U sub 2 are called parameters. To understand this method, we assume two things. We assume two crazy things, but it works. The proof of why numbers 1 and numbers 2 can be assumed is very lengthy, so I will spare you. I will tell you that it has been proven and it does work. When you get to graduate school, you have to prove all this stuff. So sometimes in this class, I prove some of the consequences, but in graduate school, we prove everything. So we just don't say this theory is true, you prove the theorem. If there's a sophisticated formula, you have to prove it. And so here, we assume that the y sub 1 and the y sub 2, now what are they? They come from the complementary solution, the y sub 1 and y sub 2. That's the same from before. So y sub 1 times this u sub 1 prime. Whenever we find out what u sub 1 is, then we'll know what u sub 1 prime is. The thing about this method is that if you recall the proof of the limit by using epsilon delta, that proof is kind of strange because the proof actually assumes the ending within the proof. You assume what you're going to get, and then you build that proof, and then once you finish with the proof, you think you're finished with it. You actually get some delta. That delta is related to some epsilon. Actually, once you get the delta, you're supposed to then really write the proof from that point. And then say, okay, assuming delta is this, then we have if the absolute value of x minus a is less than that delta, we can produce what happens out in the space. This is the same method. That is that we assume y sub 1 and y sub 2. We don't know what they are. You will run across u sub 1 prime and u sub 2 prime before you get to u sub 1 and u sub 2. So we get this so-called derivative integrated, and we can get the u sub 1 and the u sub 2. So we assume these two guys, and I'll show you how that looks. We'll look at 2 or 3 problems here today. So here are the steps that I've devised to help you, and the steps are really good. So the first thing we're going to do is you'll solve for y sub c, solve for the complementary solution. We've been doing that in chapter 4 already, so it's the same thing. So you solve for u sub 1 and y sub 1 and y sub 2, step number 1. Write the two assumptions as a system of equations. So we're going to write it like this. So the first assumption is this first line, and the second assumption is this guy. We have a system. In the system, you can solve it any way you want to solve it. Probably the easy way to solve it is just use Cramer's rule. We use Cramer's rule to solve a system when you have functions involved. If you have numbers, you just use the elimination method and you get you get the values you want. So we use Kramer's rule. So Kramer's rule would say that take the determinants, W, capital W sub 1 and W sub 2. What are they? This is the Warren scheme, capital W. So this Warren scheme is a determinant. So here we consider not the parameters, but we consider the so-called coefficients. So, and the coefficients within Kramer's rule would help us find the parameters. So capital W, it says y sub 1 and then its derivative below. And then over here, y sub 2 and its derivative below. W sub 1, if you recall Kramer's rule from algebra, says you replace the first column, that y sub 1 and y sub 1 prime, with the values on the far right, 0 and f of x. Right? Then everything else stays the same for the determinant. W sub 2 says you replace the second column with the values on the far right from the system. So 0 and f of x over there, with everything else staying the same as from the previous capital W. So step number 4, so I told you it works backwards. You first get u sub 1 prime. So u sub 1 prime from Kramer's rule is W sub 1 divided by W. Now I have this negative y sub 2 times f of x divided by W. I don't remember all that. I just remember W sub 1 divided by W. U sub 2 prime is W sub 2 divided by W. We're going to integrate step 4. When you integrate step 4, integrate this u sub 1 prime, then that'll give me u sub 1. Integrate u sub 2 prime, I can get u sub 2. Now, I don't know if you've been doing this, but I hope you do. You know, all of these lectures are already in Blackboard. Just print them out before you come to class, and then you can just fill in the information that I covered. Okay. So now, write y sub p. What is y sub p? Let's go back up again. So we assume here that y sub p is of the form u sub 1 times y sub 1 plus u sub 2 times y sub 2. So once you end up with step 4 and you integrate step 4 for step 5, then that would yield the u sub 1 and the u sub 2, then you can write your y sub p. And then finally you use the superposition principle to write the solution. That is that y is equal to the complementary solution plus the particular solution. Right? Well, let's look at a problem, and I think you'll better understand these steps. And I go through these steps step by step as we work the problem. We're going to work number 3. So the first thing we do is we solve y double prime plus y equal to 0. Well, you recall the auxiliary equation here would be m squared plus 1 is equal to 0. So we get m plus or minus I. So this implies that y sub c is c sub 1 times cosine x plus c sub 2 times sine x. So what I need from here is that y sub 1 is cosine x and y sub 2 is sine x. Step number 2, assume. Here, the formula says that assume that y sub 1 times u sub 1 prime plus y sub 2 times u sub 2 prime is equal to 0, and assume that y sub 1 prime, its derivative, times u sub 1 prime plus y sub 2 prime times u sub 2 prime is equal to f of x. Now you make sure that your f of x is your g of x divided by that a sub 2 of x. For this problem, a sub 2 is 1, so it's just 1 divided by sine x, so it's still sine x. Okay. So let's look at the system. So this is cosine x, this is our y sub 1, times u sub 1 prime plus sine x times u sub 2 prime is equal to 0. Then we look at this guy. It's the first line. This is the second line. So I take the derivative of the cosine. So I get negative sine x times u sub 1 prime plus, take the derivative of sine, I get cosine x times u sub 2 prime is equal to f of x, which is sine x. So from here, I want to extract out of there the Warren scheme. So that'll be the third step. We get the Warren scheme. So capital W is the cosine x, then below that is this derivative, negative sine x. On this side is the y sub 2, which is sine x, and its derivative, cosine x. So you know the Warren scheme is the multiplication of the crosses. So it's cosine times cosine, we get cosine squared x, and then it's minus the negative sign times sine, so that becomes positive sine squared x. For this problem, the Warren scheme here, capital W is 1. Now, it's not always the case, it's just a problem right here, right? So, W sub 1, replace the first column with 0 sine x. The second column stays the same from W, so this is sine x cosine x. So we do the crisscross for the determinant on this guy. That gives us negative sine square x. Find W sub 2. First column from W stays the same, cosine x, negative sine x. And we replace the second column with 0 sine x. Compute this. This is cosine times sine minus 0. Step number 4 says here that u sub 1 prime is equal to w sub 1 divided by w. So w sub 1 is negative sine square x divided by 1, and that's just negative sine square x. U sub 2 prime is w sub 2 divided by w. So this is cosine x times sine x divided by 1 It's just cosine x sine x. Step 5 says to integrate. So that is that u sub 1 is going to be the integral of u sub 1 prime dx. So it's a negative there. So this is negative times the integral of sine square x dx. We have strict instructions of how we integrate sine square x dx from calculus 2. Right? So if it's sine square x by itself, you have to rewrite that using a trig identity. What is it? Yes, sir. Who said that? Thank you. I love this guy, man. So, yes. So this is negative times the integral. Replace the sine square x with 1 minus cosine 2x all over 2 dx. So we integrate that. So you break that up into two parts, integrate the 1 over 2, right? So it's a negative out there. So it's negative 1/2 x. The negative times negative is positive. It's a 1/2 sitting out there, but then you have to use a u du on that cosine 2x. Let u equal to 2x. Du is 2 dx. You get a 1/2 from that. So you get 1/2 times 1/2 is 1/4. The integral of cosine is sine, and that's 2x. Naturally, it's a plus c, but we're going to take into consideration all constants from the makeup of the complementary solution. So I just put it there because we know that we ought to write it there, but it's not needed here. Okay. So this is negative 1/2 x plus 1/4. I'm going to need to rewrite that sine 2x so that when I write the solution, it simplifies well. Sine 2x can be written as what? It's a trig identity. Isn't that 2 times cosine x times sine x? Go from the double angle to the back to the single. That was the u sub 1. What about the u sub 2? That's the integral of u sub 2 prime dx. The u sub 2 prime is cosine x sine x. Cosine x sine x dx. How do you integrate that? Talking about integration, not derivatives. It's not that difficult. U du. You can let u equal to sine x, and du would be the cosine x. You can let u equal to cosine x, then you have to manipulate the negative, right? Because the du would be a negative sine x, and you don't have negative sine x, just have sine x. So probably easier to use let u equal to sine x. If u is sine x, du is the cosine x dx, So your answer becomes sine square x divided by 2, right? U, integrate u, so that's just u squared over 2. So this becomes sine squared x over 2. So hopefully you've seen that enough times in calculus 2 to know what's going on. All righty. So now y sub p now write y sub p as this, and then finally we write the final solution. So let's do step 6. So y sub p is set to be the y sub 1 times u sub 1 plus y sub 2 times u sub 2. So the y sub 1 is cosine x, and the u sub 1 is all this. So it's times negative 1/2 x plus 1/2 cosine x. What's going on? Sine x, then that's plus y sub 2, which is sine x, times u sub 2, which is that sine squared x over 2. Now we got to simplify that. A lot of stuff going on in there. So this is negative 1/2 x cosine x. I'm here with the cosine x distributed through the parentheses, plus 1/2 cosine squared x sine x, plus, this is, 1/2 sine cube x, but just write it 1/2. I want you to see what's happening. Sine x times that sine square x. Do you see some like terms there in this term and this term right here? Well, there's a common factor of 1/2. It's a common factor also of a sine x. So we just want to factor that guy out. So y sub p is negative 1/2 x cosine x plus, take out a 1/2 sine x, and then what I have left there is cosine squared x plus sine squared x. Well, cosine squared x plus sine squared x is just 1. So that just leaves us with negative 1/2 x cosine x plus 1/2 sine x. That's y sub p. Now the final answer, step number 6, is that y is set to equal to y sub c plus y sub p. So that's c sub 1 cosine x plus c sub 2 sine x plus y sub p, which we got that over here. So this is minus 1/2 x cosine x. That's the answer. You don't like it. Roger, I see your forehead, you got some waves. I saw some of the other foreheads kind of frowning up. You don't like my answer. You don't like my answer. Don't hurt my feelings. What's wrong with my answer? Is the answer good? Did I throw something away? Talk to me, David. You're a thinking man. Yes. Yes, sir. Exactly. This is C sub 2 times sine x. This is the 1/2 sine x, right? It's going to be multiples, right? You're exactly right. The C sub 2 could include that as well, right? Same form. Writing it over would be a redundance, which would give you really linearly dependent solution. And you need your solutions to be linearly independent, right? So this C sub 2 sine x would take into consideration all the forms thereof of that same type, which includes the 1/2 sine x too. So you got to watch out, Miss Lauren. All right, let's look at another one. Just can't get it on one problem. Number 5. Y double prime plus y is equal to cosine x squared. You remember the setup for number 3, I think that's what we worked at first. The homogeneous part was the same, y double prime plus y from that previous problem. So we know that y sub c is equal to c sub 1 cosine x plus c sub 2 sine x. And so, I don't know if I have to write everything out or can we just write the Warn scheme? W, this is cosine x, its derivative is sine x. The second part is sine x here, its derivative, cosine x. Just like from before, we know that Warn scheme gave us 1. W sub 1 would be 0 and the cosine square. And this is sine x, cosine x. So this gives us negative sine x, cosine squared x. W sub 2, cosine x, negative sine x. Replace the second column with the 0 and the cosine squared x. So this is just cosine cube x. Okay, this is cosine x, right, times the u sub 1 prime plus the sine x times u sub 2 prime equal to 0. Negative sine x times u sub 1 prime plus cosine x times u sub 2 prime is equal to the f of x, which is the cosine square. So that's the system by which we built the so-called Warn scheme. So this is step 1, step 2. Step 2. 3. Step 4 is the so-called u sub 1 prime is equal to w sub 1 divided by w. So w sub 1 is divided by 1, so we just write negative sine x cosine squared x. And u sub 2 prime is the w sub 2 divided by w, which is just cosine cube x divided by 1. So just cosine cube x. So step 5, I want to find the u sub 1, which is the integral of u sub 1 prime dx. So this guy is negative sine x cosine squared x, so let's put the negative there. Sine x cosine squared x dx. This is equal to, see if I have any more friends, cosine cube x divided by 3. Years ago, I used to jump on the desk to get your attention. I don't do that anymore. I have a problem with my lift. How do we get cosine cube x divided by 3? U du works a whole lot of times, right? Let u equal to what? As my driver's ed teacher, Mr. Towner, would say, equal to what, class? He had a list. If you're going to drink, do what, class? Don't drive. If you're going to drive, do what, class? Don't drive. That's all I learned in that stupid class. But anyway, yeah, so you let u equal to the cosine x, just one cosine x, right? And du picks up negative sine x. So this is u squared, right? So I'm integrating u squared dx, or u squared du, if you will, which becomes u to the third divided by 3. But u is what? Cosine. You got to be able to see it, folks. So important. You might not be able to see everything, but some things you want to be able to see. So you get it. All right. Let's look at the other one, u sub 2 prime. So u sub 2 prime is the integral. U sub 2 itself is the integral of u sub 2 prime du. So this is the integral of cosine cube x dx. What was the method of integrating if you have like cosine cube x dx or sine cube x dx? How do we write that? All right, sounds good. Say it again. Cosine x times 1 minus sine square x, right? because 1 minus sine square x is cosine square x. Are we all together? Okay. So u sub 2 is the integral of cosine x dx. Just break that integrand up. Minus the integral of cosine x times sine square x dx. So this becomes sine x. For this second integral, let u equal to sine. Du picks up cosine x dx. So that the integral of u squared becomes u to the third divided by 3. So here, this is minus sine cube x all over 3. Did you see that? Just let u equal to one of those sine x's. And you pick up what you need. So step 6 says that you can write y sub p. So y sub p is y sub 1 times u sub 1 plus y sub 2 times u sub 2. Y sub 1 was the cosine x, and the u sub 1 is the cosine cube x over 3. Plus sine x, that's y sub 2, times u sub 2, which is this expression here, sine x minus sine cube x over 3. Simplify that. So y sub p is cosine to the 4th x over 3 plus sine squared x minus sine to the 4th x over 3. Now some commonality between that cosine 4x over 3 and that minus sine to the 4th x over 3. Let's see. So this is cosine to the 4th x over 3 minus sine to the 4th x over 3 plus sine square x. So the y sub p, I'm going to simplify that. That's 1/3 times, that's the difference of two squares. So this is cosine to the 2nd x minus sine to the 2nd x times cosine square x plus sine square x plus sine square x. Well, we get here 1/3 cosine square x minus 1/3 sine square x plus sine square x. You know the cosine square plus sine square is just 1. Right? And we simplify that, just one last step here. 1/3 cosine square x plus 2/3 sine square x. So step number 7, y is equal to y sub c times plus y sub p. This is c sub 1 times cosine x plus c sub 2 times sine x plus the y sub p, so which is plus 1/3 cosine squared x plus 2/3 sine square x. Okay. Now, it's trivial, but you would need to do it. The answer in the back of the book doesn't look like that, but they're the same. So you would need to show, going from one to the other, that they are indeed the same. My smile means something. All right. One more in this section. Number 12. So the first thing we do is we want to solve the y double prime minus 2y prime plus y equal to 0. We use the auxiliary equation, so this is m squared minus 2m plus 1. We can factor that. That's m plus 1 times m plus 1 equal to 0. Implies that we have m equal to negative 1 and again m equals to negative 1. So y sub c is c sub 1 times e to the negative x plus c sub 2 times x times e to the negative x because of the repeating terms, right? Yes, sir. Oh, yes. Thank you. Sorry. Just trying to see if y'all are paying attention. I tell y'all so quiet in this class. You got some folk who just can never be wrong, right? No matter whatever you say, there is always some excuse, the reason why they're right. And, fellow was playing baseball. He was playing left field, and man, he was just having a hard time. He was just missing all these balls, and man, the old coach got mad with him and said, "Douglas, what are you doing out there, man? Yeah, I tell you what, you're so sorry. I'm gonna go out there. You come in this dugout and you have a seat." And so Douglas went on in and sat down. So the first ball that came to the coach, man, sun got in his face and ball hit him in the forehead. So the next ball that came to him, it was a drop ball. The ball bounced up and he tried to catch it, and the ball went right by him. Third ball that came to him, he thought he had it, and sitting right there, the ball hit him right in the chest. Well, the coach ran back to the dugout and said, "Douglas, you got left field messed up so bad, even I can't do anything with it." So, so look, man, I don't know what y'all doing with this problem. Anyway, so this is m minus 1 and m minus 1. So this is m equal to 1, m equal to 1. And so this is e to the x now, and this is x times e to the x. Thank you. Step number 2. So here we have e to the x times u sub 1 prime plus x times e to the x times u sub 2 prime is equal to 0. Take the derivatives of the y sub 1, the y sub 2. So the derivative of e to the x is still e to the x. Take this derivative of the product rule. So this is 1 times e to the x plus the first times the derivative of the second. So that's x times e to the x times u sub 2 prime, and that's equal to this f of x, e to the x, all over 1 plus x squared. So, step number 3 says we want to get the Warnskines. It says e to the x, e to the x, x times e to the x, e to the x plus x times e to the x. So we compute this determinant. So we get e to the 2x plus x times e to the 2x, then minus x times e to the 2x. And that just leaves us with e to the 2x. W sub 1, replace the first column with 0, e to the x over 1 plus x squared. And then this column is x, e to the x, e to the x plus x times e to the x. So the crisscross, we get 0 for the first term minus x times e to the 2x all over 1 plus x squared. W sub 2, e to the x, 0, e to the x over 1 plus x squared. So here this gives us e to the 2x all over 1 plus x squared. Step 4 says u sub 1 prime is equal to w sub 1 divided by w. So w sub 1 is that negative x e to the 2x over 1 plus x squared, and that's divided by w, that's e to the 2x. So basically the e to the 2x's would cancel out, so we have left just negative x all over 1 plus x squared. And then the u sub 2 prime is w sub 2 divided by w. This is e to the 2x over 1 plus x squared, and that's divided by e to the 2x. And so that just gives us 1 over 1 plus x squared. Step 5 says integrate what you have there, so that u sub 1 is negative the integral of x over 1 plus x squared dx. What is that equal to? Why is the x a constant? You integrate with respect to dx. It's not a constant, David. Okay? All right? Don't tell nobody else that. All right. This is the workshop. This is the laboratory, so we can make mistakes. What's this integral, folks? Natural log, right? So when you look, because let u equal to 1 plus 2x squared. So du picks up what? 2x dx. So this is going to be negative 1/2 natural log of 1 plus x squared. you come here, you got to know your calculus, because it'll show up if you know it or not. Use 2 is the integral of 1 over 1 plus x squared dx. That's tan inverse of x. So 6 y sub p is y sub 1 times u sub 1 plus y sub 2 times u sub 2. So y sub 1 was e to the x, and the u sub 1 is negative 1/2 the natural log of 1 plus x squared plus y sub 2, which is x times e to the x times u sub 2 tan inverse of x. So number 7, y is equal to c sub 1 times e to the x plus c sub 2 times x times e to the x minus e to the x over 2 times the natural log of 1 plus x squared plus x times e to the x times tan inverse of x. Okay, that's that. Well, I will try to cover 4.7 and 5.1 on Monday. We'll stop there. You should be able to do the homework now for section 4.6.